Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and take a look at our Bellwork. And so we were asked to graph each of these equations by hand. I'm going to call on you to help me out. So everybody take a look at the first equation. There's our old friend, slope-intercept form, right? Y equals mx plus b. So what's the y-intercept from that first line based on its equation? The y-intercept, right? Y equals mx plus b. What's that going to be? Nathan? -4, thank you. So we can plot our y-intercept -4 on the y-axis. And then we can count our slope number as a fraction, rise over run, to get additional points on the line. What's the slope of that based on its equation? What's the slope, Samantha? 1 over 3, absolutely. So from any point on the line, I'll go ahead and start at this y-intercept. I can count up 1 unit and over 3 units to get additional points. Up 1 unit over 3 units. I can even go backwards. Down 1 unit and back 3 units, so long as I make sure that I follow, right? I follow our slope pattern. All right, so now we'll go ahead and connect those, and we'll get our first line. So it looks like we've got, this is our first line. Great. And now the second line is not in slope-intercept form, right? Raise your hand if you remember what form that's called. What form is it when you've got x's and y's over like that? Thanks, hands down. Rachel? In standard form, right? Standard form. And standard form is useful for modeling situations that involve linear combinations, right? Like $2 for every student ticket plus $4 for every adult ticket equaled your total revenue or whatever. So that was useful for modeling that. But in terms of graphing, it was useful if we could quickly find the x and y intercepts. So slope standard form is useful for graphing because we can easily find the x and y intercepts and graph using those intercepts. And so how do I get the x-intercept? Easy cheesy. I'll simply plug in 0 for y and solve for x to get my x-intercept. If I were to do that, what makes this easy is that that y term drops off entirely, and I'm left solving the baby equation, 2x equals 9. So it looks like my x-intercept is given by 9 divided by 2 is 9 halves, and so 4 1/2 or 9 halves, comma, 0 must be my x-intercept. Let's go ahead and plot that. So 9 halves would be 4 1/2, comma 0 would be right there. Next, I'll go ahead and find my y-intercept. So my y-intercept is easily gained by doing the reverse. I'll go ahead and plug in 0 for x and solve for y. The x term drops out after substitution in for 0, and I have to solve the baby equation, -3y equals 9. Dividing both sides by -3 yields y equals -3. So it looks like my y-intercept is going to be 0, comma, -3. Let's go ahead and plot that backward. All right, so it looks like I've got my first line graphed in red. I'm going to do my second graph in black. And that was a good blast from the past, as we remember. If we remember then, standard form versus slope-intercept form. All right, so go ahead and raise your hand if you had these two pictures. So if you had these two pictures, great. So what's one point on that first line? So what's 1 point on that first line? Go ahead and share with the class. Andrew?
On the first one, there's 0, -4.
0, -4 is on the first line. Oh, show. What's another point on that first line? Another different point on that first line. Jacques?
3, -3.
3, -3. Thanks. What's the third point on that first line? Third point on that first line. Cody?
6, -2.
6, -2. Awesome. Thanks. Next line. The black line. What's an integer point on that black line? Right? An integer point on that black line. Taylor?
-4 or 4.5 comes 0.
So 4.5 comes 0. Yes. What's a different point on that black line? A different point. Blake?
-3,
-3, -5. Good. And any other points on that black line? Right? Any other integer points on that black line? Ian?
0,
-3. 0, -3. Awesome. So there's an infinite number of points, right, on each line. Today we're going to investigate what it is that makes a solution to a system of equations, and we'll be looking at that with tables and with graphs. But first, how about a blast from the past? I saw you guys talking, and I heard you talking about each of these forms. So our slope-intercept form, we know that that is number 1, the red line from our Bellwork slope-intercept form could be written a couple of different ways. We could write slope-intercept form as y equals mx plus b, where m is my slope, right, my slope of the line, and b is my y-intercept. We could also rewrite that as y equals a plus bx, where y is my equals the start value a, and then plus or minus the rate of change bx, right? And so we could also write that as y equals a plus bx, where a is my start value and then b is my rate of change. Standard form we saw in our second one. So standard form, right? Standard form was the ax plus by equals c. And that's useful for finding x and y intercepts easily. So standard form would look like ax plus by equals c. And lastly, point slope form. And I heard some people talking about this too. Remember, point slope form just comes from our slope equation. M equals y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. Except instead of using y sub 2 and y sub 1, we use y minus y sub 1 is equal to m times quantity x minus x sub 1. If you just multiply that denominator over, you get y minus y sub 1 on the left is equal to m times quantity x minus x sub 1, where m is the same old slope from slope-intercept form. It's the slope of my line. And then x sub 1 comma y sub 1 is any point on the line, right? Is any point on the line. It doesn't have to be a y-intercept, right? It can be anywhere on the line, x sub 1 comma y sub 1. Awesome. Well, that was a quick and dirty review back from Unit 2, Semester 1. I'm glad we had this stuff. All right, so we've already taken care of your reading question check. What I'm going to do is pause the recording, and we're going to go ahead and pass your test back. Okay, so I'll pause the recording. Okay, ladies and gentlemen, let's take a look at our content objectives for today. We're going to recognize properties of systems and equations. We're going to estimate the solutions to those systems by graphing, and then we're also going to solve systems using tables. So you will need a graphing calculator for later. All right, let's go ahead and take a look at what it means to be a system of equations. So everybody find on your note sheet, your day 1 note sheet for Unit 7, a system of equations is just two or more equations joined by the word and or brackets. And so typically these are easy to recognize because they're two or more equations joined together. A solution to a system is a point or points x comma y that satisfies all of the equations in the system. So when we talk about solving a system, we're talking about finding an ordered pair, a point, x comma y, that satisfies every equation in that system. As opposed to solving equations back in Unit 1, we were typically looking for a single x value, like x equals, or a single variable value, like b equals. Now we're looking for an ordered pair, x comma y, a point that satisfies each of the equations in the system. And lastly, constraints is just another name for equations, right? The equations that form the system, another name for those is constraints. So we'll use constraints or the equations in the system, we'll use those interchangeably. Take a minute to make sure you have our first definitions down, and of course the recording here will be posted as well as the exported PDF notes. And so if you didn't get some of this or you wanted more of it, you're welcome to just scroll down to the PDF and you can add that in. So what is a system of equations in this case? Well, the collection, right? The collection of these equations joined by the word and or a bracket is the system. And so this would be the system of equations, y equals 1/2 x minus 4. And 27x plus 9y equals 27. If those are joined by brackets, then that's a system of equations. In our picture, we can see that the first equation, the pink equation, is represented by the red line, right? Y equals 1/2 x minus 4. We just did one like that in the Bellwork, where my y-intercept would be -4, up 1 over 2, up 1 over 2, up 1 over 2. And then the green standard form linear equations graph is represented by the green line, right? So what does it mean to be a solution to a system? Well, we know a solution to a system is an ordered pair, a point, x comma y, that satisfies all the equations in the system. So if we're talking about the red line being the collection of points that satisfies the red equation, and the green line being all the points that satisfy the green equation, could you find a point that satisfies both equations simultaneously? You bet your boots you could. Go ahead and tell your partner the solution to the system based on its graph. Be ready to share with the class when I call on you. We're going to decide which ordered pair x comma y satisfies all the solutions in the system, and be ready to share. All right, what point did you and your partner select? Samantha and Casey?
2, -3.
2, -3. Raise your hand if you got the same as Casey and Samantha. 2, -3. 2, -3, absolutely. And so graphically, we've got a shortcut. If we can determine the point of intersection from a graph in the equations of a system, then we've generated the solution to the system graphically. So once again, 2, -3 would be the solution to the system based on the graph. However, we want to make sure that it satisfies each equation in the system and that wasn't off by a little bit. And so what can we do? We can always verify algebraically. And I would encourage you to do this on your Unit 7 quiz before you turn in. You can check every single potential answer to the system solving questions. You can check it before you turn in and know beforehand whether you're right or wrong. Let's go ahead and take 2 and plug it in for x. And so if I took 2 and I plug it in for x, right, and see what it gives me for y, it should give me -3 if we're x. So let's check. A half of 2 is 1. 1 minus 4 is -3. So it satisfies the first equation. Let's check the second equation. Again, we're going to put that 2 in for x. In this case, we'll put the -3 in for y. And let's check. 27 times 2 is 54. Plus 9 times -3 would be -27. 54 minus 27, does that equal 27? Yes, it does. So we are confident that we have found the solution to the system. Once again, to be a solution to the system, it's an ordered pair x and y that satisfies every equation, not just one equation in it. It's got to satisfy all the equations. Awesome. So that's our printable. Now let's take a look at another system. In this case, let's generate our graphs. And for now, let's go ahead and do this algebraically. So don't worry, we'll get to use our graphers later, but for now we're going to do this non-calculator. We're going to do it by hand. We're going to go ahead and make the red graph comes from the first equation, y equals x squared, and we know this is our parent function. Everybody, let's carefully plot some integer points on this first equation. We know 0, 0 is the vertex of our parent parabola squaring function. And we also know that if we go out 1, because this is a y equals 1x squared, we're going to have the same exact steepness as my parent function from unit 1. So out 1, up or down 1 squared is 1. Out 2, up or down 2 squared is 4. So everybody go back to your vertex and go out 2, up 4, because 2 squared is 4. Out 3, up 3 squared is 9. We can get some nice integer points on that first pink equation. We also know, due to the symmetry in a parabola, that each of those integer pairs could be reflected about the axis of symmetry, in this case the y-axis, and generate additional points for free. And so I'm going to take advantage of that and go ahead and reflect that, and reflect this. It looks like we've got a nice picture now of our pink equation represented by the red parabola. Let's go ahead and carefully connect those to a nice smooth curve. Next, let's consider the green graph. And so some of you are talking about point-slope form. This is point-slope form. When we go to graph an equation in point-slope form, it's oftentimes easier to determine the point x comma y that's on this graph, as opposed to rearranging this and then rewriting in slope-intercept form. That would take much longer. For example, in point-slope form, I know that my x sub 1 is this 1. And my y sub 1 is this 1. And so 1 point on this line is, because it's x minus x sub 1, and y minus y sub 1 is just 1 comma 1. So I could go to that graph and plot the point 1 comma 1. I could now count out my slope as a fraction, rise over run, to determine additional points. So I'm going to go ahead and pick out my slope. That negative sign is really -1. And so from that blue point, x sub 1 comma y sub 1 that I've already plotted, I'm going to count out my slope number. In this case, my slope number m is given by negative 1 over 1. So from this point, I can count down 1 over 1, down 1 over 1, down 1 over 1. I can even count backwards so long as I go backwards and then up, back and up, back and up, back and up, and so on and so forth. After I get several points, I'm ready to go ahead and connect them, and I'll make a green line for that second green equation. All right, so we've gone ahead and graphed the first equation in my system, y equals x squared. We've graphed our second equation, that line, y minus 1 equals negative 1 times quantity x minus 1, using point slope form. That was a pretty cool way to graph it. We started at our point, x sub 1 comma y sub 1, and counted our slope as a fraction. We were doing the same thing we did with Bellwork. We just weren't starting at the y-intercept. We were starting at x sub 1 comma y sub 1. That was pretty sweet. Jacques?
Why would the first coordinate not be negative 1, negative?
Great question. So as I look at my point slope form, I've got a y minus y sub 1 built into it, equals m times quantity x minus x sub 1. And so if I had to rewrite this equation using a point, let's say 1, 1, I would go and do y minus the y coordinate would be 1. So this would be y minus 1. Equals, we'll do negative 1 because that's one example. The slope m was negative 1 times x minus, and then what's x sub 1? That's the x coordinate for the point, that's 1. So because I have a subtraction built into my point slope form, I know that this point was positive 1 comma positive 1 because there's a subtraction already in my formula. Does that help some?
Yeah.
Awesome. All right. Let's go ahead and take a look at another. Oh wait, let's get the solutions. So let's get the solutions to this. So again, go ahead and tell your partner what's the solution to this system, and be ready to share with the class when I call on you. What's the solution to this? Okay, so what's the solution to this system? Kendall and Hannah?
1, 1.
1, 1, raise your hand if you had 1, 1. 1, 1 as a solution, good, excellent. Anything else? Negative 2 comma 4. By golly, it does look like negative 2 comma 4 is on each of those as well. Raise your hand if you also selected negative 2 comma 4. Great, so how do we know which is which? Right? How do we know which is right? Some people pick 1, 1, and some people pick negative 2, 4. Which is right? Both, and we can verify that algebraically. If I plug in 1 in for x, does 1 squared equal 1? Yes. Does 1 minus 1 is 0 equal opposite of 1 minus 1 is 0? Yes, 0 equals opposite of 0, so that checks. Let's go ahead and take a look at the second point. Is negative 2 quantity squared equal to 4? Yes, it is. If x is negative 2, when I multiply by itself, I get positive 4. Y minus 1 would be 3. Does that equal question mark? Because 4 minus 1 is 3. Does that equal question mark? The opposite of negative 2 minus 1? Let's see. Negative 2 minus 1 is negative 3. The opposite of negative 3 is positive 3. And so both of these satisfy each equation in the system. Therefore, they're both solutions to the system. That's pretty sweet. Let's take a look at another. Everybody, let's carefully sketch a graph of y equals negative x squared by hand. So once again, I'm going to go ahead and use the red line style for this. This time my vertex, 0, 0, right, represents the vertex of an upside down parabola. That negative x squared, it'll be the same steepness, it's just going to be opening upside down. And some of you had that, right, when you're talking about your test, the effect of A on the graph. And we'll go out 1, down 1 squared is out 1, down 1. Out 2, down 2 squared is down 4. So out 2, down 4. Everybody, let's go ahead and get some integer points. Out 3 from the vertex and down, you guessed it, 9, because 3 squared is 9. We'll carefully connect those. And a nice smooth parabola shape. Remember, a parabola doesn't have any corners or kinks. It's nice and smooth. We already know that a point on this line in slope, point slope form would be 1, 1. And we could count out the slope m as a fraction rise over 1 would be -1/1. So from this point we can count down 1/1, down 1/1, down 1/1. We can even count backwards if we were careful, so long as we counted back and then up, back and then up, back and then up. After getting several points, we could connect that and make a nice green graph for the green equation. Go ahead and tell your partner the solution to this system of equations. So what's the solution to this system of equations? Be ready to share with the class. So what's the solution to this system? Emily and Jacob? There's no solutions, right? There's no solutions to this system. If graphically the solution to a system is the point of intersection, then graphs that don't intersect, that share 0 points of intersection, have no solutions. Absolutely, no solutions. Good job. And so if you were asked to solve this system, you would say no solutions. Say no solutions. Awesome. Okay, let's go ahead and add 2 more terms then to our definitions. A consistent system is simply a system that has 1 or more solutions. And so if there's a solution to the system, 1 or more, right, we've seen instances of each case so far in today's lesson, then that's called a consistent system, right? There's at least 1 point that satisfies all the equations in the system. Versus an inconsistent system is a system that has no real solutions. And so if it has no real solutions, like the system we just saw, then that would be an inconsistent system. Right? An inconsistent system. So let's go ahead and label those previous 2 systems in the answer blank as consistent or inconsistent. And so we've already seen that a consistent system just has 1 or more solutions. So when we had 2 solutions, right? So all it takes to be consistent is to have at least 1 solution. This one has 2 solutions, so this would be consistent. Versus our second equation where there were our second system where there were no points of intersection, no real solutions, that's simply inconsistent. So that's called an inconsistent system. And again, that's just terminology. That's just a different way of saying that there's no real solution. So inconsistent just means no real solution. It can be used interchangeably. Awesome. Okay, so what we're going to do now is we're going to go ahead and take a look at solving systems using graphs and tables. And for this, we will be using our graphing calculator. So graphically, the solutions to a system are the points of intersection. Let's go ahead and take a look at this one. Y equals 45 minus 5x. Y equals 5 plus 3x. So what we're going to do is we're going to go ahead and enter this in our graphing calculator and take a look at the tables. Okay, so let's go ahead and enter this in our grapher and take a look at our table. If you're a good calculator neighbor, you can zoom 6, clear out your Y equals menu, make sure your plots are off. So if your plots were on, you could highlight them. You could up arrow to highlight them and press enter to toggle them off. Your plots should be off, right, unhighlighted. Now we'll enter our original equation. So we're going to enter 45 minus 5x for the first equation, y1. Our second equation will enter 5 plus 3x. We're not going to look at the graph. We're going to use tables for this one. So we're going to go ahead and use tables for this one. So what I'm going to do is I'm going to go ahead and make sure that my table set is on auto. So I'm going to go ahead and start my table at 0. And to get to table set, everybody, you use second window as table set. So second window is table set. And I'm going to make sure that I'm on auto and auto. Sometimes it's useful to make my independent variable ask so that I can plug in x values and ask the calculator to produce y value outputs that correspond with them. But for now, I'm going to go ahead and do auto. So I'm going to make sure we're on auto. Is everybody good? Auto. I'm going to start my table at 0 and go up by 1. So now when I do second, let's see. Now when I do second graph, I'll go to my table feature, and I can go ahead and scroll along those x's and see if there's any points x comma y that are on each of those equations. As I look and scan here, I'm looking for a single x coordinate that's paired with the same y coordinate each time. So I'm scanning, I'm trying to see if there's any x values that produce the same y coordinate. And as I do that, it looks like I'm not getting any, right? So what else could I try? Are you seeing any x values that are paired with the same y coordinates?
5.
5?
Yeah, 5.
So I gotta go back. Right. So you guys are saying the x value, wait for it, 5 is paired with the same y coordinate. So what point would that be? Would that be 2020? No, that would be 5 comma 20 is on the first graph, the blue equation, and 5 comma 20 is on the second graph, so the solution would be 5 comma 20. Good job. So we've got one solution is 5 comma 20. And we can copy those out as an end. And is there anything else? Well, as I go in the other direction, it looks like now I'm getting to negatives again and positives. And so I'm going to go ahead and copy that portion of the table where I saw my solution. And you guys could write that in the chart provided. We'll get that right in the middle there. There we go. So we're looking for a given x value, right, that produces the same y value in each equation. We know that x equals 5 was paired with the same output y value of 20 in each equation. So the point that the solution to that would be 5 comma 20. All right. We want to make sure that we're always verifying using multiple methods, though. So I'm still going to take this 5, and I'm going to plug it into my original everywhere I see an x and check it. So I'm still going to check this 5 into my original. 45 minus 5 times 5 is 25. Does 45 minus 25 equal question mark 20? Yes, it does. And 3 times 5 is 15 plus 5. Does that equal 20? Yes, it does. And so each of those equations is satisfied. We know with confidence that we found the solution to that system. That's pretty sweet. Let's go ahead and take a look at another. So let's try solving this system with our calculator's table feature. How should the equations look before we can enter them into our y equals menu? So what do our equations have to look like before we can enter them into our calculator? Doc? Y equals good. So everybody, let's rearrange on your paper. We need to rearrange that. In the first case, we need to solve for y. So I'm going to divide both sides by x. So my first equation, I'm going to divide both sides by x, so I get 30 divided by x is the first equation. In the second equation, I'd have to either do 2 steps. I'd either add over the y and then subtract the 1, or I'd subtract over the x and divide everything by a negative 1 to solve for y. In either case, we'll generate y equals x minus 1. Take a minute and verify that if you need to. If you were to subtract over the x, you'd get negative y equals negative x plus 1. Dividing each term by negative 1 would switch their signs, and you'd get positive y equals positive x minus 1. Everybody good? Now what are we going to do? Let's to the graphers. We're going to go to our graphers and enter these as a new system in our graphing calculator. So here we go. We'll clear out our old entries, and we'll now enter our new entries. It looks like y equals 30 over x is our first equation, and y equals x minus 1 is our second equation. Take a minute and make sure you have the correct equations entered. And then let's go ahead and go to our table feature again. So we're going to go to the table feature again. Where was table? Second graph is the table. And last time, 5 was our solution. X equals 5 was in our solution. It was paired with the same y value, right, each time. Go ahead and, with your partner, scroll and see if you can't find the solution to this system and write it as a point x comma y. Be ready to share with the whole class what we're calling you. Where's our solution to this system? Awesome. So raise your hand if you found a solution to the system. Who's found a solution to the system? Raise your hand if you found more than one solution to the system. Anybody find more than one solution? Wow, awesome. Thanks, hands down. Megan and Caitlin, what did you ladies find?
6 and 5.
6, comma 5. Is that an order pair you're saying? 6, comma 5? 6, comma 5, and what else?
-5, -6.
-5, -6. Let me scroll up and see what you're talking about. -5. Ah, it's paired with -6 in each case. Way to go. So it looks like we've got more than one place. Stop. Great. So we've got multiple places now where we've got a single x value that's paired with the same y coordinate in each equation. So a single x value paired with the same y coordinate. So we've got a -6. Is paired with, was it -5 is paired with -6 rather? There we go. And 6 was paired with
5.
Awesome. So we've got 6, 5, and I'll put that over there so I don't confuse myself. And we've got -5, comma, was it -6? -5, -6. Awesome. So let's go ahead and take a look then at our graph. And so we've already entered these in our y equals equation. Let's go ahead and take a look at our graph. So from here we can just press the graph button. And notice how we don't have more than one solution to our system, and that's evidenced by multiple points of intersection. So our table, we only saw that first one because we didn't scroll. Our graph would give us an indication as to there being multiple solutions. And so graphically, we've got multiple intersection points. There we go. And again, algebraically, we can always check our answers, and so I'd encourage you to do that. So what were our solutions again, Megan?
6 and 5 and -5 and -6.
So 6 and 5 and -5 and -6. Let's do a quick check. So does 6 times 5 equal 30? Yes. Does 6 minus 5 equal 1? Yes, and so this first one's good. Let's take a look at the second one. Does -5 times -6 equal 30? Yes. And does -5 minus a -6, that would be -5 plus a +6, does that equal 1? Yes, and so we found both solutions. Way to go. Nice work. Great job, you guys. Okay, let's go ahead and solve this system using the graph. So we're going to go ahead and create, right? We're going to go ahead and create the graph of this system. Notice the brackets connecting those equations. So there's our system. We're going to go ahead and create a graph, and then we're going to solve it using the graph. Well, again, we're looking for points of intersection that represent the solution to a system graphically. So everybody, let's take a look at that first one. If I already got this first equation in green, go ahead and tell the class the y-intercept when I'm calling you. What would the y-intercept of that first equation be? Rachel?
4.
The y-intercept of that first equation.
I thought 0 and 5.
If you did, you'd still get the same thing for the y-intercept, right? The y-intercept, y equals mx plus b, is the value of y when x equals 0. If you wanted to solve for it, you could put in 0 for x and solve for it, but that x term would drop out then, and you get y equals 0 minus 1 is? Absolutely. Visually, you can see it by looking at slope-intercept form and picking out the b value. Are you good? Let's plot that bad boy right now. So here we go, -1. Go ahead and tell the class the slope number from that first equation. What's my slope as a fraction rise over run? What's my slope as a fraction? Will? 5, thank you. So from this point, we can go ahead and count out 5 and over 1, up 5 and over 1 to get points. So here we go. 1, 2, 3, 4, 5 over 1. I can count backwards. 1, 2, 3, 4, 5 over 1. And then I can connect those and get a green graph. So my green graph will be this. Next, I'll do the second equation in red. Go ahead and tell the class the y-intercept. So what's the y-intercept of that second equation? Mark.
3.
3, thank you. What's my slope as a fraction rise over run for the second equation? Ian?
Negative 2 over 1.
Cool. Let's count down 2 and over 1. Down 2 and over 1. Down 2 and over 1. Remember, we can even go backwards as long as it went up and back. Up and back. We'll get a nice picture. Awesome. What's different about this system than the previous 3? So what's different about this system graphically than the previous 3? Rachel? They only intersect once, I agree. They only intersect once. What else is different about this system? Taylor?
It's not like an integer form.
Yeah, before when we made a graph, right? Before we made a graph, we went ahead and we counted over with our pencil tip, and we looked at the integer pairs where, like on the cross, on the little lattice coordinate grid where they intersected. And if I try to do that here, I can see the point of intersection. I know there's a solution. I know it's a consistent system. But darned if I'm going to be able to guess what that fractional coordinate is where they intersect. It's not on an integer ordered pair in my xy coordinate plane, right? So what do? Quit, throw in the gutter and go buy another? Field trip to Wanna Bowl, that's what I'm talking about. No, we're going to stay strong, right? And we're going to get that solution today graphically, tomorrow algebraically. So first let's do it graphically. We can find the solution to a system graphically using the graphing calculators by using the calculate menu and the intersect feature. Everybody, here's our steps. So let's find our steps on the note sheet. We're going to do these together. We'll solve each equation for y and enter in the y equals menu. Check. So let's go ahead and do that. So in our y equals menu, we're going to go ahead and enter our equations. So in our y equals menu, we're going to enter 5x minus 1 and negative 2x plus 3. So we've entered those in our y equals menu. Then we're going to inspect the graph and look for intersections. So I'll go ahead and press graph. I'm looking for intersections. How do we do? We did very well. Now we're going to press second trace for the calculate menu. So everybody, let's do second trace for the calculate menu. You should be no stranger to the calculate menu because it's got such old friends like maximum and minimum and 0, right? We did all those in our last test. Second calculate maximum, second calculate 0. Good. So we've got our calculate menu, and we're going to select which option we want. The fifth option, intersect. So we'll select intersect. Then we'll do first curve, enter, second curve, enter, and then use our left to right arrow key to get close to a guess before pressing enter a third and final time. Voila! It'll spit out the x equals and y equals, right, coordinates, so we can write that as an ordered pair x comma y, just like we did when we could pick out integers. So here we go. First curve, enter. Second curve, enter. Guess, enter. And it looks to me like it tells us the xy values, but gosh, how many decimal places do I keep? And if these were linear equations, right, shouldn't I have rational answers? So let's go ahead and see. I'm going to write down my x equals as much as I can. So it was 0.57142857, and it was y equals 1.857148. 9. All right. So I think that these should be rational solutions, and I don't like the fact that they're decimals here, right? They go on like that. So what I'm going to do is go to my home screen. On my home screen, I'm going to go ahead and enter that x value as much as I can. So on my home screen, I'm going to enter 0.57142857. I'm going to enter that. Enter, and then I'm going to do math frac and see what rational number this is, right? I'm going to see what rational number this is. And so let's do math fraction. Darn it! Didn't give me anything, did it? So what did I do wrong? Well, this sure looks like a pattern to me. 0.571428571428571428. What if I entered more? Will it? Yes! Victory! So I changed it back into a rational number by using the calculator math frac enter command, and I changed it into 4/7. I wonder what that y coordinate is. So it looks like I have to enter a lot, huh? 1.857142857142. I bet it's going to be sevenths because I got that same pattern. Let's try. Math, frac, enter. Yes! Victory, 13/7. So it looks to me like by changing these back into fractions, we get our final answer to over Gauge-Arm, and I'll write this as 4/7, 13/7. That was pretty sweet. So now we have a systematic method to use the built-in software from our graphing calculators to find the solution or solutions to a system of equations. And it doesn't matter if there's more than one point intersection. We can just do second calculate intersect as many times as needed. Right? Just make sure for your final guess that you go closest to the point that you're looking for. Right? Otherwise, we'll continue jumping on the same one each time. Awesome, you guys. Great work. Let's go ahead and bring it together then for closure. So think. What does the solution set to a system look like in a table? So I want to know, what does the solution look like in a table? We did that with our scrolling. Don't say it out loud, write it down, written response for everybody, and be ready to share. Versus 2. What does the solution set to a system look like graphically? So when you're looking at a picture of the graph, what does it look like? 3. How many solutions does an inconsistent system have? And 4, how many solutions does a consistent system have? So let's go ahead and make sure that we have a written response for each of these, and then be ready to share your responses on the whiteboard. Awesome. Go ahead and share with the class then, what does the solution set to a system look like in the table? So when you're looking in the table feature, what are you looking for? Chloe?
The 2 y values are the same.
Absolutely. The 2 y values are the same for a given x coordinate. And so a given x coordinate is paired with the same y values each time. So a given x value is paired with the same y value in each equation. So you get 2 of the same y values in a row. Nice job. I'm going to say in each equation then. Awesome, thank you. what does a solution set to a system look like graphically? So if you're looking at a picture of the graph, then what are you looking for? Chrissy?
The intersection of points.
Absolutely. So they're intersection points graphically. Good, thank you. How many solutions does an inconsistent system have? So how many solutions does an inconsistent system have? Jacob? Good, so no solutions, right? No solutions for an inconsistent system. How many solutions does a consistent system have, right? So a consistent system, how many solutions does that have? Maya?
One or more.
One or more, absolutely. Could have one, could have 17. Could have an infinite number. All it takes is one solution and it's now a consistent system. Good job. So one or more is perfect. Awesome. What questions do you guys have on today's closure? You guys did great, okay? So we've got our system objectives, and keep in mind that your assignment number 1 was reading questions, includes 5.3 and 5.4. I put that on the agenda. I'm gonna go ahead and stop the recording and post it to our Moodle site. You've got a nice chunk of time. You can get a lot of this done right now, and so that's a nice chance to get going on your assignment.